Good morning, students. Welcome to Complex Analysis Live Lectures. In this class, we discuss about different types of singularities and residues at a this singular points. Also, residue at infinity. Okay. Then we'll see some several examples and results. Fine. So I to simplify writing, to skip writing everything, because there are so many definitions and so on. So let's understand the topics. So I decided to prepare a Beamer presentation. Then I have copied here. Okay, fine. Now we have already seen what is meant by a singular point. So you say suppose z naught, then if you take a function f, then f fails to be analytic this at z naught. Okay, analytic at z naught. But if you take any neighborhood of z naught, any neighborhood you take, then at least, so however bigger neighborhood, however smaller neighborhood you take, at least in every neighborhood there will be one point where this f is analytic. Okay, then we say that that point is singular point. So at that point f actually is not analytic, but in around that point, whatever neighborhood you take, however small you take, at least there will be one point in that neighborhood where f is analytic. Okay. Now what is meant by a singular, this singularity is said to be isolated. So that means if we can isolate in the sense, can we keep it away from others, that word we use, isolation. Okay. So nowadays, because of this corona, this isolation, everybody know it, right? So similarly for singularity, what is meant by isolated singularity is that a singular point is said to be isolated singularity if we can find a neighborhood around that z naught, that point, such that no other point here is in this neighborhood, there are no singular points exist in this neighborhood. That means we have separated this singular point from other singular points. Then if it is possible, then we say it is isolated singularity. Okay. So a point z naught is called an isolated singularity if there exists a deleted neighborhood, because z naught obviously we cannot include. So if there exists a deleted neighborhood, okay, in such that it is f is analytic everywhere there. That means there is no other place where f is not analytic, right? That means it is same as saying that f, this point, is isolated singularity. Whatever singularities of this f, they are outside this neighborhood. Okay, let's see example. Suppose if you take f of z, which is equal to z plus 1 by z cube into z square plus 1, then obviously what are the singular points? First of all, what are all the singular points for this function? Z is equal to 0 and z square plus 1 is 0. That means z is equal to plus or minus I. At these points, f is not analytic, but we can see that if you take any neighborhood of 0 or any neighborhood of I or minus I, that we can find one of the neighborhood where these singular points can be separated. That means these 3 points are isolated singular points. Okay, why? Let me, sorry. Okay, so why this z is equal to 0, I and minus I, they are isolated singularities. If we can draw the picture, then we can understand. For example, if you take this one, so here you will have 0 and this is I, and here you have minus. We can intuitively check that if you want to make sure that, for example, take radius half, then if you take the radius half, then that neighborhood does not contain I and minus. Similarly here we can take the neighborhood around this I with radius half. Okay, then also here similarly, so you can see that these 3 singularities we can separate by a particular neighborhood. Okay, particular type of neighborhood. Therefore these 3 are singular points which are isolated. Okay. Now take another example, which is f of z. F of z is equal to 1 upon sine pi by z. Okay. So remember where this has singularities, where sine takes values 0. So sine takes values 0, sine pi by z. Sine pi by z takes values, first of all thing, this z is equal to 0, this is not defined. Okay. So z is equal to 0 is clearly a singular point. And if you take z is equal to 1 by n, then 1 by z will become n. So sine n pi, we know it, they are all 0. Right. So z is equal to 0 and z is equal to 1 by n, where n is plus or minus 1 plus or minus 2. These are all singular points. Okay. Now one can guess that whatever we have approached here, for example, here we had 3, 0, I minus I. So if we have uh, just like discrete, that means this 1, 1, 1 by 2, 1 by 3, these are all singular points. Okay. So what can we think? Whether they are isolated singular points? Because they all lie between minus 1 and plus 1. So let me draw that picture here. If you draw the picture for this one, so this is 0. Here you will have minus 1 and plus 1. Okay. Remaining all will be something like this, right? But they keep on, there will be infinitely many. Okay. So if you take any 1 by n, then that one is an isolated singularity, because we can make sure that if you take z is equal to 1 by n, then next one is 1 by n plus 1, this side is 1 by n minus 1, and so on. So if you take the minimum of 1 by n minus 1 by n plus 1, then 1 by n minus 1 minus 1 by n, because if you put this as, suppose if this is 1 by n, then this is previous one is 1 by n minus 1, and here it is 1 by n plus 1. Okay. So take their distance, and whichever is minimum, take that as epsilon. Okay. Here for example their distance is 1, so we have taken half for safe side and so on, right? Then we can see that z is equal to 1 by n. All those singularities are actually isolated singularities. Okay. So this is, they are all, each singular point is isolated singular because of this reason. But what about 0? If you we all know that this 1 by n, if you take the sequence, it tends to 0. That means there will be, after some stage, there will be infinitely many points which are available in this every neighborhood of 0, right? So that means this 0 you cannot separate. There is no neighborhood around 0 where no other isolated points exist here. Okay. So that is, such neighborhood is not possible. That means however small neighborhood we take, by using Archimedean principle, you can take that there exists a natural number such that 1 by n is less than that epsilon. Okay. So therefore at least one this singular point will be there in however small neighborhood we take. So therefore z is equal to 0 is not isolated singularity. Okay. Fine. Now we'll introduce the concept of what is meant by a residue. So what is meant by residue? For that, take z0, which is an isolated singular point. That means we can separate that with a neighborhood where f is analytic everywhere except that z0. Okay. So then there exists an R such that f is analytic at each point. Okay. And in the neighborhood 0 less than mod z minus z0 less than R. Then in few earlier classes we have discussed about Taylor's and Lorentz expansion. So in this domain, annular domain, we have what we have is called Laurent expansion. So f of z has a Laurent series representation which we can write like this. Okay, where each bn, we already know in that theorem, where each bn is nothing but 2 pi I into integration of f of z upon z minus z naught whole power minus n plus 1 dz. Okay, over C, where C is any positively oriented curve. Okay, entirely lies in this annular domain, right? So in particular, if you take B1, so this B1 is nothing but 1 by 2 pi I. This minus 1 plus 1, it is 0, so this power is 1. So what we have here is f of z dz, or this B1 is called the residue of f at z0. From this we can calculate what is b1. Using this formula we can calculate, or we can use residues to calculate the integration. That means integration of f of z over c is 2 pi I times b1, okay, where b1 is the coefficient of the term 1 by z minus z naught in the Lorentz expansion of the given function. Okay, so where this b1 is called the residue, which is nothing but the coefficient of 1 by z minus z naught in Lorentz expansion. That is the definition. So to talk about residues, we should have first singularities, isolated singularities especially. So if you take z naught is an isolated singularity, then f has Lorentz series representation, and write the Lorentz series representation, and whatever coefficient is there for the term 1 upon z minus z naught, then that coefficient is called as residue, and it is denoted by residue of f of z at z is equal to z naught. This is actually b1, where b1 is the coefficient of z minus 1 upon z minus z naught in the Lorentz expansion. Okay, let's why if you if you observe this integration formula which we have written here, integration of c f of z dz is equal to 2 pi I into b1. Such type of integration we have also seen when Cauchy integral formula. So if we know that f is analytic inside and on c, and given point z naught is interior to c, then integration of c f of z upon z minus z naught is this one. But this formula fails if f is not analytic at z naught. At that time, this residue formula can be applied to evaluate integration. That means you can see here, even if f is not analytic, we can calculate the integral using this residue given by integration of f of z. This c dz is 2 pi I into b1, where c is the given c. Okay, c is the given contour. Okay, where z naught is an isolated singularity. Okay, which is inside that. Fine. If you see the example, suppose we want to evaluate integration of z square into sine 1 by z over c, where our c is the positively oriented unit circle mod z is equal to 1. Okay, so if you take this picture, then what we have here is this is our c. So it is positively oriented, this is our c. Okay, and we want to calculate integration of this function f of z, which is z square into sine 1 by z over c, right? Clearly z is equal to 0. It is a problem. This function z is equal to 0. This is a singular point, and one can see that this f is analytic everywhere except at z is equal to 0. So we have a Lorentz series expansion. If you take the domain, mod z is strictly greater than 0. So we have a Lorentz series representation for this function, which is how we can have sin z. We know the expansion of sin z is z minus z cube by 3 factorial z power 5 alternatively plus and minus. Then what is sin 1 by z? Replacing z by 1 by z, we get this. Then multiply by z square. So what we have here is z minus 1 by 3 factorial into z plus 1 by 5 factorial into z cube minus n. So what we want is this one. Okay, because the coefficient of 1 by z minus z naught, our z naught is 0 here, so one coefficient of 1 by z, which is minus 1 by 3 factorial. So that is our b1. Okay, so therefore what is the integration of this one? Integration of this is 2 pi I times b1. So 2 pi I times b1, which is 2 pi I into minus 1 by 6, so minus pi by pi I by 3. That is the integration of this, right? So you can take one more exercise for understanding. What we can observe here is that it is not just for one residue. That means it is not about just one singularity. Suppose the function has more than one singularities, but finitely many singularities. Okay, z1, z2, z3 up to some zn. Then also we can find the integration of f of z, okay, using the residues. Residue at z1 we can calculate, residue of z2 we can calculate, and so on. Because we can find simply a smaller neighborhood where only z1 is the isolated singularity, no other are outside that, right? So that is called Cauchy residue theorem. Okay, that is due to Cauchy. So what is Cauchy residue theorem? It says that if we have a C, this is our C, okay, be a simple closed contour described in this positive sense. If a function f is analytic inside and on C, but except at finitely many points, which is z1, z2 up to zn, okay, then integration of C f of z dz is equal to 2 pi I times summation of residues of f of z at those points. Okay, see this if it has no singular points, then you can see that this sum is 0. So therefore, obviously integration of C f of z dz is equal to 0, right? So if f is analytic everywhere inside, right, it has no singularities, that we already seen that, right? Okay. So if it has finitely many singular points, then integration of C f of z is 2 pi I times sum of the residues of the function, right? How we can prove? The proof is similar. Proof is very easy using Cauchy-Residue theorem. What we require for Cauchy-Residue theorem? If we have a multiply connected domain, how we can form a multiply connected domain? So we can have, let CK be positively oriented circle at ZK. So you take each one C1, okay, they are in positive sense, okay, C2 up to Cn. We select in such a way that they are circles centered at ZK. No circle is intersecting the other, and that is always possible because we have only finitely many points. So try to find the distance, minimum distance among each zi's. Then we can have radius less than each and every one, so that they cannot intersect, right? That is always possible. So we can have this one. Now this is a multiply connected domain C together with this C case. So therefore integration of C f of z dz is nothing but, because here C and C case, they are all in same direction. So what we get by Cauchy-Residue theorem is integration of f of z dz over C minus summation integration of f of z, okay, over ck. This is equal to 0. Earlier in actual Cauchy-Residue theorem we will have plus here, but here their direction is same, so we get minus here, okay. Otherwise you write plus here, then you write minus ck, it is same, right? Okay. So that is what here. Now, but now each ck, now if you take this one for example, if you consider this cn, so you have cn, okay, and you have zn, because only in this one f is analytic everywhere except at z0, okay. So therefore integration of this one, integration of f of z over cn is nothing but 2 pi I times residue at zn, right? It is true for all this inside one. That means integration of f of z over ck dz is 2 pi I times residue of f of z at z is equal to zk. Therefore if you substitute those in summation, we get the result. So Cauchy residue theorem says that if there are finitely many singularities inside that curve C, okay, and f is analytic on C and everywhere except those finitely many points, then integration of f of z over C is 2 pi I times sum of those residues, okay. Quickly we'll try to understand with an example. Take f of z, which is equal to 5z minus 2 by z into z minus 1, okay, and where our circle C is mod z is equal to 2, okay. Now clearly z is equal to 0 and z is equal to 1, they are the singularities, okay, they are inside this C, okay, and you can easily see that they are isolated singularities because we can separate them by smaller neighborhoods. So z is equal to 0 and z is equal to 1, they are isolated singularities, both lies inside this C, and f is analytic everywhere else inside C except at those 2 points. Therefore we can apply this Cauchy residue theorem. Therefore integration of this one is nothing but sum of, so residue, so this integration of whatever f of z dz is what, residue of f of z at z is equal to 0 plus residue of f of z at z is equal to 1. Now, if we want to find residue of f of z at z is equal to 0, what we want to write? We want to write the f of z in this Lorentz expansion. Okay. And then we want to find the coefficient of 1 by z, because here z naught is 0. And similarly, we will try to write the Lorentz series expansion, which involves the coefficient of 1 upon z minus z naught, which is 1 here. So 1 by z minus 1. Okay. That we have already seen when we discussed about examples. So take this function f of z. Somehow we should write this one as we have to consider 0 less than mod z less than 1. Okay. This is the annual region, right? Now, there is no problem with this z. So we have to write this z minus 1 as 1 minus z. So take minus 1 common. And using this, you expand. So 1 by 1 minus z, we know already. 1 by 1 minus z is summation z power n. So this is nothing but minus you get here. Okay. Then you multiply by this 5z minus 2 by 2, which is same as 5 minus 2 by z. Then again multiply these two internally. What we get here is this, okay, which is 2 upon z. So the coefficient of 1 by z is 2. So residue of f at z is equal to 0, the value is 2. Similarly, we want to calculate residue of f at z is equal to 1. So then we have to consider the different annular domain, right? So that means now we will consider z minus z naught, which is 1. So that is less than 1. But this is same as 1 less than mod z less than 2. Okay, that is this picture here. Okay, so you take z, mod z is less than 1 and less than 2. So here. Okay. Now, so how we can write the Lorentz series expansion? So somehow we should be able to write this 1 is less than mod z. This implies 1 by mod z is less than 1. Okay, so mod z less than 2. That means mod z by 2 is less than 1. So in our expansion, we want to make sure that these terms will come. Okay, so for that, here what we did is z minus 1, 5z minus 2 upon z minus 1. Here z minus 1 plus 1. Okay, z minus 1 plus 1. So we have added and subtracted 1 and minus 1 here. So this is just like 1 upon, so see whatever z is here, for our z is nothing but z minus 1, just like here. Okay, right. So we are trying to write this in this form. So what we have here is 1 by, here when plus is there, alternatively sign is there. Okay, so that is here. Then you multiply this and try to find the coefficient of z minus 1, which is 3 here. So coefficient of z 1 upon z minus 3 is 3. So therefore residue of f of z at z is equal to 1 is 3. Then sum of the residues is 5, and 2 pi I times is 5 is 10 pi I. Okay, this is the integral value. And later in this class itself, we will see that this problem can be easily simplified further using other method. Okay, so suppose if we have here 4 residues, 4 singular points, okay, or 5 singular points, then we have to every time calculate residues, then we have to use sum. Okay, instead we can use another concept, then we can simplify further, that we will see in this class later. Okay. So take these exercise problems. Find the residue at z is equal to 0 of the following functions. Okay. And use Cauchy residue theorem to evaluate this one. Okay. So here z is equal to 0 and z is equal to 2. They are singularities. Here try to find what are the singularities and so on. And then calculate using Cauchy residue theorem. Now we will move to what is meant by residue at infinity. So far whatever we have seen, z is equal to z naught, where this z naught is a complex number. Now we will find what is meant by residue of f of z at z is equal to infinity. That means point at infinity. Okay. So if you remember, when we define what is meant by neighborhood of point at infinity, they are all mod z which is greater than 1 by epsilon, like that, right? For whatever small epsilon greater than 0, right? So take an analytic function is said to have an isolated singularity at infinity. Okay, at infinity, if f is analytic throughout the region r greater than mod z. Okay, so if there exists an r such that, so you take mod z, so this is mod, if you suppose this is r, okay, this much is r. So if mod z greater than r, that means everywhere here So if f is analytic everywhere outside this circle, okay, then we say that f has isolated singularity at infinity. Okay, because you can understand why we are saying that it is an isolated singularity at point at infinity, because this above somewhere is, because a complex plane together with that infinity, we will call it that, right? So this is like infinity. Now you can see that f here, the neighborhood we can find in such a way that f has no other singularities in this neighborhood. Okay, that's why we call it this as an isolated singularity, right? Fine. Obviously we know infinity is, for this complex functions, infinity is a singularity, right? Oh. Now what we do is we'll try to give what is formula of residue of f at point at infinity using residue at z is equal to 0 of some new function which is 1 by z square into f of 1 by z. Okay, if you remember, we have seen some relation between how to deal with limits involving infinity and limits involving only complex numbers, like this here. Okay, it is similar to this. So what is the following theorem? It says that if suppose our f is analytic everywhere in the finite plane, that means our complex plane, except for a finite number of singular points interior to that positively oriented curve C, then integration of C f of z dz. Okay, so what we have here is this statement is similar to the statement of Cauchy residue theorem. So we have a C here and f is analytic except at finitely many points. So except this z1, z2, zn, remaining everywhere this f is analytic. Okay, at that time integration of C f of z dz is, Cauchy residue theorem says that 2 pi I times summation residues, sum of the residues. Here this integration of C, this integration of f of z dz over C is 2 pi I into residue, a single residue evaluated at z is equal to 0, but of new function which is 1 by z square into f of 1 by z. Okay, so what we can see right straight away, the difference between Cauchy residue theorem and here, this simplifies the integration easily, because there if you assume that there are 10 residues are there, then you want to find the values at all those 10 points, then you have to sum that and then multiply by 2 pi. Whereas here, no matter how many residues we have, but what is required is only finitely many. Then this value integration can be calculated using only residue of a new function at z is equal to 0. Okay, proof is not a difficult one. The idea is very simple. Let's understand this picture here. So take C, this is our C. Okay, so we have C here. So this is our C. I'll draw that picture here so that we can understand. So first we have C here. This is our C. Okay, now what we can do is we can take a circle, okay, which encloses this C. That means because f is analytic inside this C except at only finitely many points, right? So we can take R1 a large enough. So we will take the R1 radius in such a way that when you take the circle, okay, around origin, then that circle completely encloses this given circle mod z is equal to, okay, the mod z is equal to r. So you see, suppose if this is C, see that origin may be outside, inside, wherever. So suppose I'll put it just like this. Okay, then this r1 we can select in such a way that, so this picture only you take. So this is our origin, this is our r1. So now if you construct this circle, okay, if you construct this circle, this completely inside this circle our given curve C is there. Okay, what is the advantage of this one? Then this f is analytic if you take f, because f is analytic throughout the domain r1 greater than mod z greater than infinity. Okay, because whatever f we have, f is analytic everywhere in the finite plane except for finitely many number of singular points, which are of course interior to C. So whatever singular points f has, they are all inside this. Okay, that means if you take anywhere here, so anywhere here if you take, then f is analytic everywhere. Okay, so therefore f is analytic in this annular region which is mod z bigger than r1, of course fine. Okay, so therefore it has f of z as a Lorentz series expansion. So and not only that, the point at infinity, if you see here whatever I have explained in this picture, from that it is similar to this, right? From that we can see that infinity is a isolated singularity. Okay, so therefore now take C naught. This C naught in what we can say clockwise direction. So consider this C naught which is in a clockwise direction, okay, and whose radius is r naught, which is bigger than r1. Okay, so that is our, let C naught denotes this circle mod z is equal to r naught oriented in clockwise direction, okay, which is bigger than r1. Then because this C naught, whatever we are talking about, this C naught in clockwise direction, we are taking in clockwise direction. So if you see something, what is meant by clockwise direction? If you stand there on that circle C naught, what you will get to left side? That means whatever direction means you stand, your face should be in this direction. Okay, then left side means if you stand, anyone, a person can stand here, okay, and facing to this side, then what will be left side? Left side is this one. That means interior is nothing but this one. Okay, interior is nothing but this for that C naught because of this direction orientation. Okay, when you have, say for example, C, then what is this? C is anti-clockwise direction. So this C is anti-clockwise direction. So if you stand here and see, then whatever left hand side is this one, that is interior. Okay, whereas for interior to C naught is this part, whatever we have written just like sun, that is our interior to C naught. Okay, so interior will change if you change the direction. Okay, so fine. So what we have observed is that this, since C naught lies inside this mod r1 less than z less than infinity, the residue of f at infinity we can calculate. The residue of infinity is integration of f of z C naught dz. This is 2 pi I times residue of f of z at z is equal to infinity. Okay, again I repeat how we have defined residue. This is nothing but, whenever we want to talk about residue, we want a function should be analytic in the domain mod z greater than some r. Here our r is r naught. So if you take in this r1 which is here, okay, then in this annular region, this residue of f at infinity can be calculated using this C naught. Okay, fine. Now again, as f is analytic throughout the closed region C, now you take C and C naught. This is C and what we have here is C naught, right? So this is our C and this is our C naught, right? And f is analytic everywhere in between. Okay, so therefore integration of by using the deformation path, integration of f over C is same as integration of f over C naught. Okay, fine. But only thing is, when we want to apply the deformation path result, both should be in same direction. But C and C naught are in reverse direction, so one you will get minus. That's all. So integration of C f of z dz is integration of f of z dz minus C naught, which is same as minus of integration f of z dz. Only reason is this C and C naught have different, they are different directions. Okay, fine. So therefore, if you combine this one and this one, what you get is integration of C f of z dz is minus 2 pi I, because integration of this C naught f of z is minus times integration of C f of z dz. So therefore, minus 2 pi I times residue of f of z at z is equal to infinity. So the idea is, now we want to calculate residue of f of z at z is equal to infinity, right? So we will try to write this Lorentz representation of f of z in this region, annual region, mod z bigger than r1, less than infinity. Okay, we'll denote that by summation cn z power n, where each cn is given by, we know already, 1 by 2 pi I times integration of f of z upon z power here n, this is minus n plus 1. Okay, n here n is equal to 0 plus or minus 1 and so on. So this n plus 1, okay, over what? Here whenever we want to define, then that curve should be in positive orientation. But because our C naught, whatever we have considered, is in clockwise direction, so what we get here is minus C naught. Okay, this is dz. That's all. Where n is any integer, 0, plus or minus 1, plus or minus 2, and so on. Right? That means for all positive values, this is z n plus 1. For all negative powers, this is z minus n plus 1. Right? Now, why we want to have this z and 1 by z? If you observe here, integration of the residue involves integration of f of z dz. When you want to move it from infinity to 0, then we should go with d of 1 by z. That, as I said, limits when you are dealing a point at infinity to point at 0, the function should be 1 by z, right? So we not only want to find f of 1 by z, f of 1 by z into f of 1 by z, because residue of f of z at z is equal to infinity is this one. But if we want to find residue of a new function, which is d of 1 by z, okay, then that will be residue at z is equal to 0. Residue of this function, new function, whatever we are going to get, that is like this. So I'm just explaining the idea how suddenly this 1 by minus 1 by z square f of 1 by z is coming. That is because of this d. This differentiation is also there. Okay. So I'll just remove this part so that we don't confuse. But how it is coming, that suddenly you may ask, sir, why we want to multiply by this 1 by z square? Where it is coming? This 1 by z square is coming mainly because of this integration dz f of z dz. Okay. So when you are dealing with infinity and 0, z should be replaced by 1 by z. And when you have this d of 1 by z, differentiation of 1 by z is minus 1 by z square into dz, right? So that's why that minus 1 by z square term is coming. So replace z by 1 by z in this representation, Lorentz series representation. Where is it? Here. Okay. Then multiply by 1 by z square or minus 1 by z square. It is not a problem. Now you can see that our region is changed here. Our region is changed here. It is 1 by z. Okay. So 1 by z square into f of 1 by z, then you will get this one. Okay. So you simply take this z inside z power n plus 2, then you rearrange this n plus 2, you use it like n plus 2 is equal to some m, then this will become cm minus 2, then z power m. Okay. And when you change this, you will get this. So from r mod z to infinity, we got a final 0 mod z less than 1 by r1. Okay. This is new function which is 1 by z square f of 1 by z. Okay. Therefore, residue of this function at z is equal to 0 is the coefficient of 1 by z. The coefficient of 1 by z, which is c, when you substitute n is equal to 1 here, c minus 1. So c minus 1, right? That is same as 2 pi I integration of f of z dz minus c naught. That means when n you substitute n is equal to minus 1, this z power 0, which is 1, right? Fine. So therefore, integration of c naught f of z dz is minus will come here, minus 2 pi I times residue of this new function 1 by z square f of 1 by z. Okay. Now take this b, which is this, and take the above one, which is a here. Okay. Then you can see that integration of c naught f of z dz, here also integration of c naught f of z dz. So therefore, these two will be equal. Okay. That means residue of f of z at z is equal to infinity is minus times residue of z is equal to 0 at 1 by z square f of 1 by z. That is this, right? And of course, integration of f of z is 2 pi I times residue of this. Okay. Yes. Remember, integration of C naught and integration of C, they are minus to each other. Okay, because of the directions are different, right? Now, so what we have seen is using this residue at infinity, our Cauchy residue theorem has become simpler. That is the advantage of having this residue at infinity, right? No matter how many singularities it have, till it have only finitely many singularities, we can apply the result, or we can take the help of residue at infinity and we can calculate. For example, take this example which we have already calculated. At z is equal to 0 and z is equal to 1, two residues we have calculated, then sum we have taken. Okay, but because here we have only at z is equal to 0 and z is equal to 1, okay, by mod z is equal to 2, if you take, then 0 and 1 they lies inside this circle. Okay, and these are the only two places where f is not analytic. Okay, so therefore we can have integration of this 5z minus 2 by this z. This is z into z minus 1 dz. This is nothing but 2 pi I times residue of this f of 1 by z, 1 by z square into f of z, z is equal to 0. Okay, this is the result which we have seen here, right? Okay. So we can calculate whatever this f of z, try to find 1 by z square into f of 1 by z, and we want to have residue at z is equal to 0. That means we want to find the, in Lorentz expansion, we want to find the coefficient of 1 by z. Okay, so we have to simplify this. It is not a difficult one. We have to simplify in such a way that 1 by z term will come. That's all. Okay, so you using this 1 by z minus 1, you expand this, which is 1 plus z square, z cube and so on, then multiply internally. Okay, and what we are getting here is this, this is the term which we require, that 1 by z, coefficient of 1 by z is 5. So therefore coefficient of 1 by z is 5, which is residue at z is equal to 0 of this new function, right? So therefore the integration is 2 pi I times that residue, which is 10 pi I, right? So previous problem and here it looks small, right? But if you have more residues, then you will actually see the difference of usefulness of this result. Okay, fine. Now we come to the last section in this class, which are nothing but isolated singularities. We can classify into three categories. Isolated singularities. So I don't want to, I'll just explain in brief so that you can understand. Okay, we can have it in three different forms, and that based on our Lorentz expansion of the given function. So because this z naught is a isolated singularity, so you write f of z in this form. Okay, so this is the f of z, okay, where our annular region is 0 greater than mod z minus z naught less than r, for some r, right? In this, whatever these factors we have, these powers are negative powers of z minus z naught, this terms, this part, we will call it that as a principal part. Okay, so depending on this principal part, we can classify these isolated singularities depending on principal part, that they are called, you can call it here a pole, okay, and removable singularity, removable isolated singularity, and essential singularity. Okay, what is meant by a pole? If this principal part contains finitely many, so non-zero but finitely many points. So suppose b1, b2 up to bm, in such a way that bm plus 1 onwards, bm plus I is equal to 0 for all I greater than or equal to 1. That means bm plus 1, bm plus 2 all are 0, but bm is non-zero. Previous one of them, suppose say b1, b2 up to bm minus 1, some may be 0, some may be non-zero, but the moment bm is 0, non-zero, and bm plus 1 onwards, they are all 0, then we say that it is a pole of order m. This is a pole of order m. If there are the coefficient of z minus z naught whole power m, if it is non-zero, after that all remaining terms are 0, then we say that it is a that particular isolated singularity is a pole of order m, and if m is equal to 1, that means only 1 by z minus z naught term is there, remaining all terms negative powers are 0, then we say it is a simple pole. Okay. Now when we say that something is a removable singularity, this removable singularity means all bn's are 0. Okay, for all n. That means the principal part in your Lorentz series expansion, no principal part exists, then we can say that that singular point is actually a removable singularity. Okay. Now when we say that it is an essential singularity, if there are infinitely many bn is not equal to 0 for infinitely many. Bn are not equal to 0 infinitely many. So if there are finitely many, then we talk about pole. If there are infinitely many non-zero terms, then it is an essential singularity. If there are no terms, there are no terms in principal part, then we say it is removable singularity. Okay, this is what I have explained, and these are the definitions. If bn is equal to 0 for all n, then we say it is a removable singularity. Okay, that means that point is a removable singularity, and your expansion looks like Taylor's expansion. No positive, no negative powers of z. Okay, these three are there. You can quickly see examples. For example, if you take f of z is this function and simplify this, you can see that here there is only one term which has negative powers of z minus 2. Okay, so therefore it is a simple pole. Simple pole at z is equal to 2, because z is equal to 2 is an essential singularity, right? And this Lorentz expansion has only one term, therefore it is a simple pole. Okay. Now if you take another example which has a pole, for example, take 1 by z square into 1 plus 1 by z square into 1 plus z, which has a pole of order m, which is 2 at z is equal to 0. Why? You try to write this in Lorentz series expansion. This means we want to see whether how many terms will be there in the principal part. Okay. So if you expand this, you will see that this is one term and this is another term, and this is the z power m, where m is not equal to 0. After that 1 by z cube, 1 by z power 4, they all are 0 here. Okay. So therefore this has a pole of order 2. So remember, even for example at present, if this is not there, this is not there, at that time also you can say that it is a pole of order m, because m, which is 2, no matter whether 1 by z term exists or not. For a pole, what is required is, when we say it is of order m is m, then that mth power, it should be non-zero, and m plus 1, m plus 2, all those powers 1 by z powers, okay, they are all should be 0, right? Of course in our here it is not that case, both 1 by z and 1 by z square, because so many times what we think is that if it is of order m, then 1 by z minus z naught should exist, 1 by z minus z naught square up to 1 by z minus z naught whole power m. We sometimes we think that all these should be non-zero. It is not necessary. What is necessary is that this should be non-zero, and after that whatever we get, they should be all equal to 0. Okay, so before this m, some may be 0, some may be non-zero. It may happen that all may be non-zero, or all may be 0, some may be 0. So there is no condition before m. At m we have a condition, and after m we have a condition for a pole, right? Now if you see another example, take this 1 minus cos z upon z square, and try to of course clearly z is equal to 0 is a singularity. So which type of singularity, if you want to check, you write this, it's Lorentz expansion. Okay, here you see z square, z power 4 and so on, and this is a constant, right? So there are no negative powers of z, that means no principal part exists. That's why this z is equal to 0 is a removable singularity for this function. Okay, now similarly if you take f of z is equal to e power 1 by z, similarly clearly z is equal to 0 is a singularity here, essential singularity. And if you start expanding this, you will see that there are infinitely many terms which contains principal part. Okay, principal part, this infinitely many negative powers of z's are there, right? That why this z is equal to 0 is an essential singularity. Okay. Fine. So these are the some of the examples you can take so many times in any competitive exam. Which type of singularity is this? It will come. Okay. So if you can classify, we can classify this using. So you should know very well to write the Lorentz series expansion. Okay. If you can write the Lorentz series expansion, then you can see whether it is a pole, whether it is a removable singularity, or whether it is a essential singularity. Okay. In next class, we'll see more about this pole, and then we'll go to zeros of an analytic function. Then we'll relate, do we have any relation between zeros and poles? Okay, that we'll see in next class. Okay, we'll stop here.